Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we're happy to have Nick Harvey here. Those of us who've been here a long time know Nick from a long time ago when he was a developer here before he started working with Lotsie and decided to go back to graduate school, and now he's getting out of graduate school. So, and maybe we'll get him back. So he's at MIT, and he's going to be talking about query lower bounds for matroids via group representations.
Thanks very much for the introduction, Jennifer, and thanks for the invitation to speak here. So I'd like to tell you today about some work I've been doing over the past few years about the computational complexity of matroids. And more generally, my research is about algorithms for combinatorial problems of practical and theoretical significance. So before I get into the main result of my talk, I'd like to start with some definitions and descriptions of what matroids are and highlight their importance in combinatorial optimization and describe some of their connections to other areas of mathematics and computer science. So what is a matroid? Matroid is basically a family of sets defined over some ground set S. So S will be a finite set, and script B will be a collection of subsets of S. And the collection must satisfy this exchange property, which is a bit of a mouthful to process. So let me illustrate this in the context of an example. So suppose we have a fixed connected graph G, and we'll let the ground set S be the set of edges of G. Then the family B will be the family of all edge sets of spanning trees of G. So for example, we may take, so in this example here, we've got a blue spanning tree and a red spanning tree. And the exchange property is saying that if we pick any edge that's blue but not red, for example, we might pick this edge here. So we pick that edge and we add it to the red set. Then what the exchange property is saying is that we can pick some other edge that's red but not blue and remove it, and now we get a different spanning tree. So this is the general defining property of matroids. So let me also tell you some terminology. The sets in this family B are called bases, and they all have the same cardinality, just like the fact that every spanning tree in a graph has the same cardinality. And this cardinality is called the rank of the matroids. So
in this definition, B equals A?
Yes, but then this is vacuously satisfied. Okay. So although the definition of matroid seems very abstract, they're actually very useful for several reasons. So one reason is that they generalize many natural graph optimization problems, and I'll tell you more about that shortly. Another reason is that they have beautiful polyhedral properties, and that makes them very useful as building blocks in a variety of contexts, for example, in approximation algorithms. And classically, it's been known that matroids relate to constructions in coding theory. And more recently, there have been some very interesting connections between matroids and the field of network coding. And I'll tell you a little bit about that now. So for example, let's look at multicast network coding. So so we have a directed acyclic graph, which has a distinguished source node and a collection of sink nodes. And the goal is to try to multicast information from the sources to the sinks at the maximum rate possible. So for example, perhaps the source has two symbols of information, A and B, and it can transmit them on its outgoing edges. And we continue transmitting them through the graph. And now the interesting thing about network coding is that a node in the middle of the network who receives several pieces of information can code them together and send that the coded symbol on any of its output links. So for example, here we're sending the sum of A and B. And then I'm sure this example is familiar to you, so using this code, we can transmit all the information from the sources to the sinks. And generally, it's known that there are efficient algorithms, efficient deterministic algorithms for constructing optimal coding solutions for multicast network coding. And so there's an algorithm using flow-based ideas due to Jaggi and several other co-authors, some of whom are sitting in this room. And I had a similar algorithm using matroids in the same year. Well, actually, this was a couple of years earlier. Okay, so now let me tell you about another interesting connection between matroids and network coding. So suppose now, instead of having a single multicast source, now let's suppose we have several sources. And what we desire is that the source A wishes to transmit to its corresponding sink, and similarly SB wishes to transmit to TB. Okay, and this is exactly the same example that we just saw, just reformulated a little bit. So the same coding solution works. Okay, so now I'd like to flip things around. So suppose we reverse the directions of all the edges, and we swap the relationship of each source and its corresponding sink, like this. Okay. Now imagine a flow solution to this problem. So not a code, we're just doing multi-commodity flow. So clearly, if a flow solution existed in the original graph, then a flow solution exists in this reversed graph, GREV, just by reversing all the flow paths. So, and also our coding solution continues to work because this graph is very symmetrical. So one might suspect that in general, a coding solution can be reversed. But the surprising answer is that it cannot. So there's an example due to Doherty and Ziegler, which I find very fascinating. And they show that there exists a graph whose reverse does not have a feasible coding solution. And this is what the graph looks like.
Oh my God.
It's a monster. And I won't expect you to figure out.
I guess they knew what they were doing. They didn't just pull this one out of a hat.
That's right. So
Is that proof that this is minimal?
I don't know whether it's minimal,
Oh my.
but I do know how they constructed it. So they constructed it using a synthesis of the Fano and non-Fano matroids. So there's some very interesting phenomena happening here about how matroids lead to interesting constructions in network coding. So I won't talk more about that today, although I'd be happy to tell you more about it later on. So now I'd like to switch to looking at discrete optimization problems. So this is my roadmap for what discrete optimization looks like. Or
Is it reversible? Sorry.
Okay, so there are many problems that are probably familiar to you. And the problem that we're going to focus on in this talk is matroid intersection. So matroid intersection, it's a central problem in this field. As I said earlier, it generalizes many classical problems. And it also has very interesting generalizations, such as submodular function minimization. So what is matroid intersection? It's very simple. Suppose I have two matroids, M1 and M2, on the same ground set with base families B1 and B2. We'd like to decide, do they have a common base? Is the intersection of their base families empty or not? And this problem has been studied for a long time, dating back to the work of Edmonds in the 60s. And there are many efficient algorithms known for solving this problem. So for example, there's the algorithm of Edmonds and Lawler, which uses omega n times r squared oracle queries. So I need to tell you what these parameters are. So n I'm going to use to denote the number of elements in the ground set, so the cardinality of our set S. And r is the rank, which I defined earlier, the size of a base. And their algorithm works in a certain oracle model, which I'll define shortly.
Can you just go back to the definition of matroid intersection?
Sure.
Okay, so.
I actually forgot what the definition of the base is.
So a base is a member of B. A base is a member of B, and the
Any member of B?
any member of B. And the family B is structured. It has to satisfy this exchange property. Remember, we're switching the edges of the spanning trees. So the family B has some structure, and the elements of B are called bases.
So the elements of S are called edges?
In the graph context, they were edges, so you could call them elements. Let's say elements of the ground set. Okay. So
The rank is the smallest base?
all bases have
All
the same
All of
size.
them are the same. They all
Oh,
have the
because of the
same
exchange.
because of the exchange.
Right, right. Just like all spanning trees in a graph have the same number of edges. Yeah. Okay, so the running time is parameterized by the size of the set S and the size of any member of the family B. Okay, and then more recently, algorithms were developed for a certain subclass of matroids known as linear matroids. And I won't tell you precisely what the definition is, but essentially, instead of working in an oracle model, you work with a concrete representation of the matroid, and the algorithm can also be, the running time is a polynomial in the length of that representation. So I won't get into the details there, it's not relevant for this talk. And there's also a weighted version of matroid intersection where you have weights on the elements of the ground set, and you'd like to find a maximum weight maximum weight base that's in the two matroids, for example. And again, there's classical algorithms known, and algorithms that are polynomial, weakly polynomial, so they depend on the log of the weights. And then also I gave an algorithm that's a pseudo-polynomial. So for very small weights, this is the most efficient algorithm known for linear matroids. Okay, so after I was working on these algorithms, one question that I was often asked is, can you show that these algorithms are optimal? So for example, perhaps Cunningham's algorithm is optimal in the oracle model, and perhaps my algorithm is optimal for the linear matroid model. So this is the question I'd like to address in the rest of the talk. Before doing so, let me tell you some general facts about computational lower bounds. So in unrestricted models of computation, like Turing machines or random access machines or circuits, proving strong lower bounds is currently beyond our techniques. So for example, 3-SAT, the canonical NP-complete problem, we think it requires exponential time to solve, but we can't prove anything better than linear time right now. So certainly proving a superlinear lower bound for a problem, a natural problem in P, like matroid intersection, that's hopeless with current techniques. But if you look at concrete models of computation, then you can prove interesting lower bounds. So for example, the input to your algorithm might be encapsulated in a black box such that your algorithm can only perform structured queries to the data. And in such scenarios, then you can prove lower bounds. For example, the classical sorting lower bound is exactly in this framework. And then there's also the well-known result on deciding monotone graph properties by Rivest and Villemin, and other such results. So as I was saying earlier, matroid intersection is often formulated in this oracle context, and I'll tell you more about that shortly. So in this work, we aim to prove query lower bounds for matroid intersection. And I also have some generalizations to submodular function minimization, but I won't talk about that here. Okay, so what is this query model I've been mentioning? So imagine we have a matroid, and it's encapsulated in this thing that looks like a 9-volt battery. And our algorithm is interacting with the matroid in the following way. So the algorithm gets to choose some subset of the ground set, and it passes it to the matroid. And the matroid says, can we extend this set to a base in the matroid? So this is known as an independence oracle. And let me again tell you about it in the context of spanning trees. So if our base family is the set of spanning trees of a graph, then what the algorithm is doing is specifying some subgraph of that graph to the matroid. And the matroid is telling us, can this subgraph be extended to a base, a spanning tree? So is this set of edges a subset of a spanning tree? In other words, is this set T an acyclic subgraph of G? So this is exactly what the oracle is telling us. Okay.
So ahead of time,
Yes?
the algorithm is informed what the set S is.
Yes, yes. I mean, it can represent this set. Perhaps it has some canonical indexing of the elements of the set S. So you can always think of them as the numbers 1 through n or something like that.
And then you're given n.
So we know n, we know the size of S, and we can index its elements somehow. That's right.
Do we have as much memory as we want?
Well, I mean, it depends on what your goal is, I suppose. So if you're
Because I could try to sort of slowly collect information so that I can actually build the matroid, right?
Yes, exactly. So so one question is, how many queries would it take you to do so? So if I allowed you to perform as many queries as you like, then certainly you could reconstruct the entire matroid. But there are examples of matroids where this would take an exponential number of queries. So in fact, the number of matroids on a given ground set is doubly exponential. So any description of the matroid must have exponential length. And so if you want to find the entire description, then that will take you exponentially many queries.
So your lower bound would be information theoretic.
Yes. I mean, well, the lower bound that I'm now describing to Christian is information theoretic. But the lower bound I'll present in the rest of the talk is not. Okay. So we're going to work in that query model of computation. Now let's talk about algorithms. So this classical algorithm of Lawler's that I mentioned earlier, it uses n times r squared queries to solve the matroid intersection problem.
Which one is this?
Gene Lawler. Gene Lawler.
Gene.
Yes. He was. He worked also on scheduling, and he was a professor at Berkeley. Okay. So Lawler had this algorithm, and then in Welsh's 1976 book on matroid theory, he posed the reasonable question: Is Lawler's algorithm optimal? So are order n times r squared queries necessary to solve the matroid intersection problem? It's a reasonable question. And the answer turns out to be no. So in 1986, Cunningham gave another algorithm for matroid intersection, which uses blocking flow type ideas, so similar to the Hopcroft-Karp bipartite matching algorithm, and uses n times r to 1.5 queries. So the answer to Welsh's question is no. So now this raises the question, can one prove any non-trivial lower bound on the number of queries needed to solve matroid intersection? Perhaps Cunningham's algorithm is optimal now.
Is R given upfront, or you have to figure it out?
Pardon me?
Is the rank given upfront for the matroid?
Well, you could always figure it out by growing a base. So R queries, n queries suffice. N queries suffice. Yeah. So you could essentially assume without loss of generality it's given up front. Okay. So now let me tell you about the trivial lower bound for this question. So it's always good to start with what are the trivial things you need to know first. Well, the upper bounds for matroid intersection depend on both parameters n and r. So we should expect that the lower bound should also depend on n and r. And the trivial lower bound is for matroids of rank 1. And it's essentially a simple adversary argument. So it says that you need to make at least n queries to each matroid in order to decide the problem. So that's a total of 2n. And by some padding arguments, you can extend it to matroids of larger rank with a commensurate decrease in the quality of the lower bound. Okay. So Cunningham's... pardon me, Oded?
It's not the expected number of queries, it's the worst case?
Worst case. Worst case, that's right. So worst case for deterministic algorithms. So throughout this talk, I'll just be talking about deterministic algorithms, not randomized.
Can you repeat why for rank 1 it requires 2n?
Okay, so I didn't explain it, but I could do so if you like. So essentially, you can think of rank 1 matroids as bit vectors of length n, and you're given 2 bit vectors of length n, and you're trying to figure out if they have a 1 in corresponding locations. So essentially taking the bitwise AND of these 2 bit vectors and deciding if it's 0 or not. Does that make sense? Okay.
But that is true also for randomized. It's like
Well, you could say that.
decide if you have.
Well, you could say that you expect to find a collision earlier. I mean, within constant factors, it's the same. Okay. So one can also take essentially the mirror image of this argument using what's known as dual matroids. And you can show that for matroids of rank n-1, in fact, exactly n queries are needed to solve matroid intersection. And it's the same sort of argument. And again, Cunningham's upper bound has a mirror image as well. Okay. So if one is trying to prove strong lower bounds, where should you look? Well, obviously, you should look in the middle, matroids of rank, say, n/2. And by padding, you can always shift things around. So for matroids of rank n/2, what we currently have is a lower bound of n from the trivial lower bound. So now let me make an implausible conjecture. So we know the exact answer for matroids of rank 1 and for matroids of rank n-1. So perhaps the linear interpolation of those 2 points is the optimal answer. Unlikely, but not previously known to be false. So in this work, what I show is the first non-trivial lower bound for matroid intersection in the 32 years since Welsh posed the problem. And my lower bound is for matroids of rank n/2, I show that 1.58n queries are necessary. 1.58n queries are necessary. So this disproves the implausible conjecture and improves the lower bound from n to 1.5n for matroids of rank n/2. So here's the formal statement.
It doesn't disprove, though, that it would be at least the bound in the other direction, right?
Sorry, I don't understand the
Doesn't
question.
Upper
disprove-
bound?
Right.
He's
What's
doing
about-
lower bound.
Right, but if you would do upper bound, then you could still go back to the picture.
Okay.
So
Upper bounds are way
it
far
doesn't
away.
disprove that it could act, that you could have a lower bound in this whole region under the dotted line, right?
Yes. So the lower bound, you could have a lower bound
You prove a better
like
lower
that,
bound than
and then
the
slightly
conjecture.
above. Yes. Yes. So for this
So I would
small
only
triangle,
not
it's
say
better.
that the conjecture is false if you prove something which is stronger than the conjecture.
Oh, so I was saying that perhaps this is the right upper bound.
Oh, I see.
Right. Yeah. Yeah. So this pink line cannot be the right upper bound because the lower bound goes above it.
Yes, I thought
Okay.
it was a lower. Just
Okay.
So there's still no news for those of us who are less concerned about the constant.
That's right. That's right. So I mean, my hope when doing this was actually that I'd get a lower bound of n log n, but the log n became a log 3. So
in some cases, so for n equal 3.
that's right. That's right.
No, there's a little over.
Okay, so here's the formal statement. So we have this family of matroids of rank n/2, and our number of oracle queries that's necessary to decide matroid intersection for 2 instances in this family is at least log base 2 of 3 times n minus lower order terms. Okay. So how could one prove such a result? Well, the first step is to think up a family of instances that are somehow intuitively hard for this problem. And often for lower bounds, we can imagine what's hard. The trouble is finding something that we can analyze and show is hard. So to analyze the instances I defined, I'm going to use tools from communication complexity. So I'll assume this is something you've seen before. We've got two parties, Alice and Bob, who are collaboratively trying to solve the matroid intersection problem. And Alice has one matroid, and Bob has the other matroid. And so then we're going to measure the number of bits of communication between the two of them. And communication complexity is very useful. It's kind of like the Swiss Army knife of complexity theory. It has a lot of tools. And one of the tools gives us a way of reducing this question about the number of queries to a certain rank computation question. So there's a matrix which one can define from the family of hard instances. And the log of the rank of this matrix will give a lower bound on the number of queries. So then the hope is that the hard instances that you defined, perhaps they have some nice algebraic structure that will facilitate this rank computation. And indeed, that's what we'll do. So let me now tell you about the hard instances. So they're actually very, very simple. So we're going to look at bipartite matching in graphs that are almost too regular. So they have exactly 4 vertices of degree 1. So in this graph, for example, we could ask, does it have a perfect matching? And of course, it does, because it has 2 paths of odd length, and odd length paths always have a perfect matching. So here the answer is yes. However, if we change the instance slightly, now we have 2 even length paths. And even length paths don't have a perfect matching. So this is a maximum matching in the graph, and it's not perfect. So the punchline is these instances will have a perfect matching. Well, they won't have a perfect matching if there's a path from vertex 1 to vertex 2. And otherwise, they will have a perfect matching. So is that clear? So essentially, we're just trying to decide, does this bipartite graph have, so it'll have, all vertices have degree either 1 or 2. And there's exactly 4 vertices of degree 2. So there's exactly 2 paths in the graph. And so if we look at the connected components, they're either paths or cycles. And there's exactly 2 paths. We're trying to figure out if they have odd or even length.
So, is this an example where there are 2 matroids? What are the 2 matroids that you're...
OK, good question. So there's a lot of technical content in this talk. So I'm trying to sweep as many things under the rug as possible. So that's one of the things I'm trying to sweep under the rug. But it's very simple. So are partition matroids familiar to you?
Well, if you want to sweep it under the rug, that's fine with me.
OK.
I'm not familiar with partition matroids.
OK, so there's a very, the most trivial class of matroids is partition matroids. And the intersection of 2 partition matroids is precisely bipartite matching. So that's what's going on here.
Partitions of the ground set are matroids?
That's right. So you have some, well, yeah, I mean, it would need some definitions. So yeah, so I probably shouldn't get into it due to time constraints. Yeah. All right, but I'd be happy to talk to you about it later on today. OK. So let's keep going, if that's OK with all of you. So this bipartite matching question can be reformulated in the following terms. And this is the viewpoint I'll use for the rest of the talk. So here's the problem. So Alice is given some permutation pi and in the symmetric group Sn. And Bob is given some permutation sigma. And here's what we're trying to decide. Are these 2 fixed elements of the ground set, say 1 and 2, in the same cycle of the composition of pi and sigma? So let me illustrate that with this picture. So I've got here pi going from left to right, and sigma inverse going from right to left. And we're looking at the composition. So let's trace out the composition from vertex 1. So from vertex 1, we go here and then here. We hit vertex 3. Then we go back to vertex 1. So in this case, elements 1 and 2 are not in the same cycle of the cycle structure of the composition. So this example is a no instance for this problem. Okay, so that's the problem we're looking at. And now, as I mentioned, communication complexity allows you to look at a certain rank computation question. So this is it. So we've got a matrix C, a 0-1 matrix, and its rows and columns are indexed by permutations in Sn. And the entries of the matrix are 1 if pi and sigma form a yes instance, and 0 otherwise. So it's 1 if their composition is in this set G, where G is the family of all permutations that have 1 and 2 in the same cycle. So G is something I'm going to use for the rest of the talk. So here's its definition. All right, and if that definition is a bit of a mouthful for you, then another way of stating it is that C is just the adjacency matrix of the Cayley graph of the symmetric group with generating set G. All right, now we'd like to understand the rank of C. And fortunately, this question of understanding the spectra of Cayley graphs is very well understood. So this is really one of the central ideas in constructing expanders. And the typical approach is to use Fourier transform or representation theory type ideas to analyze the spectrum. And that's exactly what we're going to do here. And that will allow us to show the following result. So the rank of C has the following closed form expression. So it's this double summation of multinomial coefficients with some other factors plus 1. And moreover, we show that the matrix C is diagonalizable. All of its eigenvalues are integers, and they can all be precisely computed. So if we just sum up the number of non-zero eigenvalues, then that's the rank of the matrix. And that's exactly what we do. So the corollary, now going back to the communication complexity lemmas, the corollary is that the number of queries is at least the log of the rank of this matrix. And we can estimate the asymptotic rate of growth of this expression as a function of n. And
where does the 3 come from? Log 3?
Okay. It comes from the multinomial coefficient. So if we look at, this is a multinomial coefficient of dividing n into 3 parts. And when is such a multinomial coefficient maximized? Well, it's maximized when all those 3 parts are the same. And its value is about 3 to the n. So that's where it comes from.
You somehow divided it into n parts, but that wouldn't come in anyway.
Yeah.
Okay.
So, well, yeah.
There's a power 2, so why is it not?
Good catch. Okay, so this is another thing I'm trying to sweep under the rug. You actually lose a factor of 2 in this reduction from here to here, but I was hiding it. But this is, yeah. So the loss of a 2 cancels out that 2, but very good catch. Yeah. Okay. So for the rest of this talk, I'd like to go over the proof of this result. And I think it illustrates a lot of nice ideas from algebraic combinatorics. And it shows how they can be used in a seemingly unrelated area of combinatorics, namely combinatorial optimization in matroids. So there's a number of definitions that I need to get through to do so. And for those of you who have seen this area of math before, it should be quite familiar and easy to follow. And for those of you who haven't, well, I hope it'll give you a taste of the exciting tools that they have to offer and how it can be used in seemingly unrelated problems. Okay, so to start off, let me tell you about Young tableau, or Young diagrams, is a synonym. So given a partition lambda, so a partition is just a finite sequence of integers, and the sequence is non-increasing, and the integers are all positive. Then a Young diagram is simply a drawing of boxes in the plane, left aligned, such that row I has exactly lambda sub I boxes. And the total number of boxes, well, let's call that n. Next, standard Young tableau is simply a bijection of the integers 1 from n into these boxes, such that the rows increase from left to right, and the columns increase from top to bottom. So our main result can be reformulated as follows. The rank of the matrix C is equal to the number of standard Young tableau with n boxes, whose third row has length at most 1. and some other minor conditions. So if there weren't this constraint, then you'd have an n log n lower bound. But because this constraint pops up, you get log base 2 of 3. Okay. So that's the definition. Okay, now let me tell you the main technical steps. So, and they're all fairly easy. So the first step is,
So now you will prove to us this statement that the rank is...
yes, yes. Okay, so we're going to now decompose this set G. So for starters, let's decompose Sn. So we're going to do this sort of inductive construction of the symmetric group. So the first claim is that any permutation pi in Sn can be uniquely decomposed as a permutation in Sn minus 1 together with a transposition. And let me illustrate this with an example. So suppose we have the blue permutation, pi tilde, in S6, and now we want to get a permutation in S7. Well, we just need to decide where is 7 going to go. And so if I add the transposition 7, 3, that says 7 should go after 3. So this is very simple. And another way of stating it is as follows. So if I define x sub I to be the set of transpositions j comma I, where j is less than I, and for those of you who know group theory, so you can think of this as a member of the group algebra of the symmetric group, then the entire Sn can be generated by taking the product of those xi's. And if you're not familiar with the group algebra, just think of these as sets, and think of this as taking the Cartesian product of the sets. And then whenever two transpositions come together, you take their product as a permutation. Okay, so this is just a restatement of what I said on the previous slide. Is this clear? Okay, good. So now, so here's an example. So we start with 1, we add the element 2. Now we decide where 3 is going to go. Now we decide where 4 is going to go, and so on. So every one of these transpositions is coming from one of these xi's. Okay, so now we can do the same thing with G. The only difference is instead of having x2 here, I just have a single transposition, 1, 2. And when that happens, so when I build a permutation this way, 1 and 2 start off in the same cycle, and they remain in the same cycle throughout. So the punchline is that G can be expressed as this product. Okay. So now we've decomposed G. Now let's look at decomposing this matrix C. So this is very simple. So this is the definition of C that we saw earlier. And here's an example of what it might look like. So now let's condition this definition on a particular choice of element from G. So instead of saying that the composition should be in G, we'll pick a particular element tau. And we're just going to look at the pairs whose composition is exactly tau. So we get a strict subset of the 1s from this matrix, and we get this matrix. So I'll call this matrix R sub T. And for people who know about this is just the regular representation. Okay, so the punchline is that C can be expressed as the sum over taus in G of these R matrices. Okay, so this is standard sort of trick. All right.
So the only nasty thing with this is that half tau is not. Is that also self-adjoint? No.
Is R of tau self-adjoint? No. No.
Right. So in your picture it seems to be, but
Let's see. Well, I guess it. Let's see. Is it self-adjoint?
self-adjoint.
No, it's not self-adjoint. Yeah.
Right? Unless tau is the identity, it should not be self-adjoint.
That's right. That's right.
So the picture is also.
Yeah, so I guess this is a coincidence. Yeah. So I guess it depends how you relabel things. Okay, but what it'll turn out that well, the interesting things happen when you sum over the taus. So that's what we're going to do. Okay. All right. So now let's look at decomposing R. So essentially, we're going to do. You can think of it as doing the Fourier transform to R. So we've got this fixed matrix R, and the claim is there exists a change of basis matrix B such that changing to the basis B, R becomes block diagonalized. And these blocks are called the irreducible representations. And for those of you more familiar with Fourier analysis, you can think of these as the characters. And say in the hypercube case, these characters are indexed by points on the hypercube. And in our case, they're not. They turn out to be indexed by the Young tableau. So we can pick any shape lambda, and we have an irreducible representation corresponding to lambda. In fact, it may appear several times. Okay, so this is the decomposition of the R matrices. So now we just only have one step left to go. We're going to, so here we block diagonalized R. Now we're going to fully diagonalize the xi's. So let's look at that. So recall the definition. The xi's are just these sets of transpositions. And now I'm going to define something that's a mouthful. So I'm going to define this matrix y sub lambda of xi. And it's got this messy definition. Let me illustrate it with a picture. So R sub tau is this matrix here, as you recall. And applying the Fourier transform, you get this block decomposition. So now all I'm going to do is I'm going to sum over the taus in xi. And all of the R sub taus are block diagonalized. So their sum is also block diagonalized.
The B could depend on tau,
right? No. There exists. So you can fix up front a good change of basis matrix B. So
okay, that's because, okay.
yeah. So
Because the
B.
irreducible representations of Sn.
Right, they're canonical. I mean, you can choose different Bs. In fact, I'm working with this. So there's a particular choice of B that's good for me called Young's semi-normal representation. And that's what I'm going to use. But you can just think of picking some good canonical B up front. Okay, so we saw that for one R sub tau, we get this block decomposition. So certainly for the sum of taus, we do. And so what was this y sub lambda of xi thing? Well, it's just I choose some lambda, and I just look at this block corresponding to lambda. So that's the definition of y sub lambda of xi. All right, so now here's the interesting fact. The fact is y sub lambda of xi is actually diagonal. So we haven't just block diagonalized things, we've completely diagonalized things.
So is that due to your special choice of B, or is it when if?
Yes. So for a specific choice of B, so for Young's semi-normal representation, x sub I, this matrix is diagonalized. Right, so if I chose a different one, a different B, then it might not be diagonalized.
So, I mean, this tells me in group theoretic terms that this whole thing must be a trace or something like that. Because traces are...
No, it's more than a trace. So this is stronger than analysis with traces because I can tell you exactly what all of the values here are not all the same. They can have different values on the diagonal here, and I can tell you exactly what all of them are, but they're not equal. So this is not a constant times the identity. This is some diagonal matrix with many different values on the diagonal. Okay, so now the remainder of the argument is to figure out what are these diagonal entries. All right, and they are known. So let me tell you a little bit about that. So let's look at this matrix y sub lambda of x4, say. And so first of all, we should figure out what are the rows and like how many rows and columns are there of this matrix. And so they have an interesting connection to Young tableau. So if we fixed a particular tableau lambda, then there are some standard Young tableau of this shape. And it turns out that the rows and columns of this matrix are indexed by these standard Young tableau. So there's a row T2 corresponding to standard Young tableau T2, for example. Okay, and now we can figure out what these diagonal entries are. So the claim is that in the diagonal entry corresponding to tableau Tj, we can find its value as follows. We look for the number 4. So let's look at T1, for example. So we look for the number 4 in T1, and here it is. And it's in row 2 and column 1. So we take 1 minus 2 plus 1, and we get 0. So it says that this diagonal entry should be 0. And similarly over here, 4 is up here in the corner, so we get 3 and 3. So this is precisely what y sub lambda of x4 is. And you get it just by looking at the structure of these standard Young tableaux. And there's a name for this thing here that I'll use later. It's called the content value. OK, so those are all the technical pieces we need, and now we can just wrap up the entire argument. So first of all, let me argue that C can be diagonalized. Why? Well, we saw in step 4 that these y sub lambda matrices, all of them could be diagonalized, and I just told you what the diagonal entries are. So certainly their product is also diagonal. And now this operator y is actually a homomorphism, so we can do the multiplication before applying y rather than after applying y. And in the first step, I told you that G could be expressed as this product. So now we've got that y sub lambda of G is also diagonal. Now, what was the definition of this y sub lambda matrix? Well, it was one of those blocks in the block diagonalization of R. So this is really just by definition that we've got that this matrix is diagonal, because I've just told you all its blocks are diagonal. And now in the first step, I told you that C could be written as the sum of the R's. So we're done. So C is diagonalized in this Young semi-normal basis. OK, so C is diagonal, and now we can just percolate things through and figure out what the diagonal entries are. So what are the eigenvalues of C, the diagonal entries of this? So first of all, we can look at what are the diagonal entries of these Y matrices. And we want to know when are they non-zero. So this is how we're going to compute the rank. So when are they non-zero? Well, recall that y sub lambda of G was this product of the x sub I things. So all we need is that all of these y sub lambda of x sub i's to be non-zero as well. And if they're all non-zero, then this will be non-zero. And we know what these things are. I just told you their characterization. It says if we look in the location of I in a certain standard Young tableau, then this content value thing should be non-zero. All right, so we're just moments away from finishing here. So here's a picture of what the content values are. Say this is your tableau you're working with, and it's the column number minus the row number plus 1. So they're constant on these negative sloping diagonals here. And we want them to be non-zero. So this is the forbidden diagonal here. So what it's saying is, in order for this entry to be non-zero, then what must we have? Well, we want elements to avoid this red diagonal. And in fact, we need it for all I at least 3. Well, 2 can go in there. That's fine. But now we're forbidding all other entries I greater than 3 to go there. So what's that saying? It's saying that the length of the third row must be at most 1. So the punchline is that the rank of C, so the number of non-zero diagonal entries, is just the number of standard Young tableau with lambda 3 of most 1. And some other conditions I swept under the rug. OK, so that's the end of the proof, computing the rank of C.
Can you tell me what the particular, I mean, if I had a general set of, and it's a general set G, then the sum of all R taus not be diagonalized, because probably you couldn't find one matrix B which diagonalizes all the R taus. Right?
So you're saying
what is the particular structure of G you use to get your
yes.
whatever you call it normal representation.
Right. So this is the key fact here, that G has this decomposition in terms of these elements x sub I. And these x sub I turn out to be fundamental objects in constructing Young's semi-normal representation of Sn. So there's this surprising connection between this set G and Young's semi-normal representation. So that's what enables this proof to go through.
Do you need the 1, 2, or would it be true if you had some more general G, which is of this tensor?
Well, so the x sub i's are all diagonal in this basis. So any polynomial in those x sub i's would work. And this is sort of, it's almost an x sub I, so it's just as good. Yeah.
I see. So if we had the x2 and x1, it would be fine as well.
Yes. Yeah. So x2 certainly works here. Or you can take just x5 times x7, that's equally good. You could pick and choose any polynomial in the xi's works.
I see, and you can.
And this is a special case.
If instead of x4 I would put a particular permutation, would that be allowed as well?
Not necessarily. No.
Well, maybe we should take this off.
Right.
I think
Okay. So how are we doing for time? Okay. All right. So that's the end of the proof. So now let me tell you about some future directions. So generally, I think it would be interesting to look at more uses of matroids in approximation algorithms. So there have been lots of examples of them being useful. For example, the work of Kuller and Vishkin in the early 90s, and the work of Promil and Steger on Steiner tree, and the recent work of Gomans. So there's lots of interesting work there. I think this may be a fruitful direction for other approximation algorithms questions. Perhaps TSP is a natural candidate to look at there. Also, I mentioned to you briefly at the beginning this connection between matroids and network coding. And this is, I think, really an amazing area that's just getting started. And I think there are lots of really beautiful questions to look at there, and I intend to do so in the upcoming years. And finally, lower bounds. So I think that now is a great time to look at lower bounds in discrete optimization. So we have many tools at our fingertips that weren't accessible just a few decades ago, like communication for complexity, for example. And I definitely intend to continue looking at matroids and submodular functions. But there are several other problems that I think would be amenable to this sort of analysis. Now to wrap up, let me just summarize what we talked about today. So we studied lower bounds for matroid intersection, which is, as I told you, a fundamental problem in combinatorial optimization. And to analyze it, we used tools from theoretical computer science, such as communication complexity, and tools from mathematics as well, group representations. And using those, I was able to show the first non-trivial lower bound for Welsh's question from 1976. And finally, I think that there are several applications of combinatorial optimization ideas in computer science that are very interesting. For example, the network coding. And I think that this will be a fruitful direction for researchers in combinatorial optimization for many years to come. So thanks very much for your attention. Any questions?
In your oracle model, you ask a question whether a given set is an independent set or not.
Yes.
Wouldn't it make sense to ask another question whether a given set is a spanning set or not? Because, I mean,
Is a spanning set or not?
yeah, whether it contains a basis.
So I mean, there are several oracle models for matroids. Perhaps the one that I use, the independence model, is the most studied one. And there are various connections known between the two. So it's known that there are some problems you can do with one oracle that you can't do with another oracle, and so on. So I mean, it's fair. So actually, the oracle that you defined.
Yeah, but I'm asking both questions. I mean, but you should be allowed to ask both.
So actually, the lower bound applies to your model as well. So any,
Can you use both? So some questions on spanning and some of independent?
yeah, so you can ask any question that returns a Boolean answer, and the lower bound applies for that model. If you use a stronger model, so for example, you could use what's called a rank oracle. So you specify a subset of the ground set, it tells you the rank of that set. That oracle reveals more information. Its answer is not Boolean. So it doesn't apply there. But it does apply to any Boolean oracle.
And what do you expect the truth to say for the rank of n over 2? What power of n log n?
Good question. So I believe, in fact, for the family of instances that I defined, that n log n is the right answer. So, and there's, I mean, intuitive reasons to expect why that should be the case, and that was why I pursued this whole analysis.
No, but in general, what should be the truth?
So I believe it should be possible to prove quadratic lower bounds. So something of like n squared. Yeah, n times r, or n squared. That should be doable, but communication complexity definitely cannot take you any further than that. So there's there are these notions of non-determinism and so on in communication complexity, and you can use them to show that you cannot prove better than quadratic lower bounds. So, but I think quadratic may be doable. But you need to look at richer families of matroids than the simple ones that I defined. Yeah, Fahad?
So you mentioned this has some application in minimizing submodular functions.
Yes.
So what's the result you get?
Okay, so I could say two things here. So one thing relates to Yuval's question. So if you showed a lower bound of, let's say, q queries for matroid intersection in this model, then you get a lower bound of q over log n queries for submodular function minimization. So for example, if I could prove the quadratic lower bound that I was just saying to Yuval, then you get a almost quadratic lower bound for submodular function minimization as well. Okay, so that's one connection. And the other answer to your question is, so Michelle and I have proven a result recently that relates to constructing the lattice of minimizers for a submodular function, and we have a quadratic lower bound for that. And I can tell you more about this offline.